In today's lecture, we will talk about the first separation technique, liquid chromatography. In this lesson, you will learn the concept of chromatography separation, the components of liquid chromatography, and the types of liquid chromatography, and the place theory and rate theories to understand liquid chromatography. Chromatography is the separation of individual components of a mixture. In principle, the mixture is loaded on the stationary phase, which can be solid or fluid. The individual components can be separate from each other due to the differences in the strength of chemical stationary phase interactions. The adsorption, partition, affinity, and differences among molecule weights can affect the separation process. Let's introduce the basic components of chromatography: stationary phase, mobile phase, and separated molecules. The stationary phase can be a solid phase or a layer of a liquid adsorbed on the surface of a solid support, while the mobile phase is always composed of liquid or a gaseous component. If the mobile phase is liquid, then it is called liquid chromatography. If the mobile phase is gas, then it is gas chromatography. There are many different kinds of chromatography, from column chromatography, ion exchange chromatography, gel permeation chromatography, affinity chromatography, thin layer chromatography, HPLC and UPLC, and gas chromatography. We will go through these techniques in the following slides. Column chromatography separates substances based on the differential adsorption of compounds to the absorbent because the compounds move through the columns at different rates, which allows them to get separated in fractions. This technique is commonly used for protein purification. Ion exchange chromatography, or ion chromatography, is a process that allows the separation of ions and polar molecules based on their affinity to ion exchangers, which can be anion exchanger or cation exchanger. The principle of separation is thus by reversible exchange of ions between the target ions presented in the sample solution to the ions present on ion exchangers. Two distinct mechanisms, ion attractions and ion exclusion, would determine the interaction between charged analytes and ion exchanger. Gel permeation chromatography is also called gel filtration or size exclusion chromatography. In gel permeation chromatography, the stationary phase is a porous matrix made up of compounds like cross-linked polystyrene, cross-like dextrons, polyacrylamide gels, agarose gels, etc. It is a technique in which the separation of components is based on the difference in molecule weight or size. The molecules in the samples are pumped through specialized columns containing microporous packing material. The basis of the separation is that molecules above a certain size are totally excluded from the pores, while smaller molecules access the interiors of the pores partially or wholly. The flow of the mobile phase hence will cause larger molecules to pass through the column, whereas smaller molecules will be retarded according to their penetration of the gel. Affinity chromatography is a type of liquid chromatography for the separation, purification, or specific analysis of sample components. It utilizes the reversible biological interactions or molecular recognitions called affinities, which refers to the attracting force exerted in different degrees between atoms which cause them to stay together. The examples of affinity interactions are antigen versus antibodies, enzyme versus substrate, receptor versus a ligand, and protein versus a nucleic acid. Thin layer chromatography is a technique used to isolate non-volatile mixtures. The experiment is conducted on a sheet of aluminum foil, plastic, or glass which is coated with a thin layer of absorbent material. The material usually used is aluminum oxide, cellulose, or silica gel. On completion of the separation, each component appears as spots separate vertically via the capillary action. The LC system is composed of mobile phases, uh, LC pumps, an autosampler, an analytical column, a detector, in our case, is a mass spectrometer and a computer system to record the data. This figure illustrates the structure of the LC column. The stationary phase of LC column is typically a granular material made of solid particles, and the particle size ranges from 2 to 50 micrometers. At the initial phase of LC development, most LC was performed using a solid support stationary phase containing unmodified silicate or alumina resins, which is now referred to as normal phase chromatography. Reverse phase chromatography, the most commonly used chromatography techniques nowadays, contains hydrophobic stationary phase such as C18 or phenyl groups. The functional groups coated on the silica surface will determine the selectivity of the column. However, there may be some bare hydroxyl groups on the silica, which may cause undesired interactions, secondary interactions with the analytes, and those result in peak tailing. To resolve this potential issue, some manufacturers further modify the uncoated hydroxyl group to avoid secondary interaction. This is an uncapped column. In this example, the polar group is used to encap the C18 column, allowing the use of 100% aqueous phase. Otherwise, the strong hydrophobic interactions among the C18 branches would not allow the polar analyte entering, resulting in a poor retention for highly polar analyte. The effect of uncapping procedure is illustrated in this figure. You can notice that the analyte amitriptyline show the peak tailing effect when using a non-uncapped C8 column, and this tailing effect was eliminated when using a densely bounded and uncapped column. Overall, the column's efficiency can be determined by the type of surface, the pore size, the particle size, column length, and inner diameter. These elements are illustrated in the bottom figure. The column is packed with particles which have tiny pores. In between these pores, you can find the functional grooves dangling around. Depending on the properties of your analyte, you should select the appropriate column for a better separation efficiency. For instance, if your analyte is highly polar and hydrophilic, then you can consider to use a HILIC column. If you'd like to separate the structural isomers, then C30 column may be a better choice. Hydrophilic interaction chromatography, HILIC, operates with the characteristics of the three major LC methods, including the reverse phase, normal phase, and ion exchange chromatography. The type of organic solvent and buffer, such as acetonitrile, used in HILIC is compatible with the traditional reverse phase chromatography. Like a normal phase LC, HILIC has a polar stationary phase, and lastly, the HILIC incorporates the ionic interactions with charged compounds, which is a shared characteristics with ion exchange chromatography. Multiple interactions are involved in the HILIC mechanism, including the hydrophilic partitioning, hydrogen binding, and electrostatic interactions. HILIC is a variant of normal phase liquid chromatography, but using the solvents that are miscible with water. A typical HILIC application uses acetonitrile at a concentration between 50 to 95% in an aqueous buffer such as ammonium formate, ammonium acetate, or layer acid, which have high solubility in organic solvents. HILIC can be used with many detection techniques, but when combined with electrospray ionization mass spectrometry, for example, HILIC will also enable higher sensitivities. There are many advantages of HILIC. HILIC is suitable for analysis of hydrophilic compounds and has an improved mass sensitivity because of the better dissolution efficiency. Besides, using high percentage of organic solvents usually comes with a low bed pressure. Lastly, the sample dissolved in highly organic mixtures, such as the eluent of SPE, can be directly analyzed. In this slide, we will compare the high-performance liquid chromatography with ultra-high performance liquid chromatography. In HPLC, particle sizes of the stationary phase are typically between 3 to 5 micrometer, while the UHPLC is characterized by particles of 2 micrometer or less. As with particle sizes, there is a corresponding reduction in column dimensions with UHPLC. A typical HPLC column has the internal diameter of 4.6 mm and a length of 250 mm, while the UHPLC column has internal diameter of 2.1 mm or less and is much shorter, like 100 millimeters, for example. UHPLC runs at much higher, lower flow rates than HPLC. UHPLC usually with the smaller particles and reduced column diameters compared to HPLC, leading to higher back pressure. HPLC instruments typically operate at maximum pressures of 400 to 600 bar, while UHPLC instruments can operate at up to 1500 bar. Narrow peaks are produced with a UHPLC, requiring a detector that can keep pace and provide the required number of data points per peak for detection. Most modern detectors, though, are capable of detection speeds of up to 250 Hz, which is sufficient for both HPLC and UHPLC. Using UHPLC can drastically enhance the chromatography separation. For example, to achieve a peak resolution of 4.29 between peak 2 and 3. The total runtime is 20 minutes when using the HPLC column. However, the total runtime significantly reduced to 2.5 minutes, while achieving the same peak resolution when using UPLC column. The UPLC run further improved the sensitivity by 3.4-fold. Just a reference, we can calculate the peak resolution by dividing the retention time difference with the average of peak width. We will discuss it in our following lectures. You may hear the other term, UPLC, which is actually referring to the same technology. The only difference is that UPLC is Waters Company's trademark. In the following slides, we will introduce two theories to explain the chromatography behaviors. Plate theory, developed by Martin and Synge in 1941, and rate theory, proposed by Van Dimter in 1956. The plate theory supposes that the chromatography column contains a large number of separated layers called theoretical plates. Separate equilibrations of the sample between the stationary and mobile phase occur in these plates. The analyte moves down the column by transfer of equilibrated mobile phase from one plate to the next. It is important to remember that the plates do not really exist. They are a figment of the imagination that help us understand the processes at work in the column. The plate theory provides a way of measuring column efficiency, either by stating the number of theoretical plates in a column, n, the more plates the better, or by stating the plate height, the height equivalent to a theoretical plate, which is the smaller the better. Assuming that the peaks follow the normal distribution, we can calculate the number of theoretical plates using this formula, where Tr is the retention time and W is the peak width measured at baseline. The maximum column efficiency can be described using this formula, where Nmax is the maximum column efficiency, L is the column length, and dP is the particle size. The smaller the particle size, the higher the column efficiency. On the other hand, the longer the column, the higher the maximum column efficiency. This figure shows that different column dimensions may have the same maximum column efficiency, while the smaller the particle size and the column length, the shorter the total runtime. The first important prediction is the band spreading. Given the same number of theoretical plates, the peak width is predicted to increase as its retention time increases. The second prediction is that the smaller the theoretical plate height, the narrower the eluded peak. Given that the column length is a fixed value, the smaller plate height will cause a large plate number. A larger plate number will result in a decreasing peak width. It is not unusual for a chromatography column to have millions of theoretical plates. Columns often behave as if they have different numbers of plates for different solutes present in the same mixture. The rate theory is a more realistic description of the processes at work inside a column, taking account of the time taken for the solute to equilibrate between the stationary and mobile phase, unlike the plane model, which assumes that equilibrium is infinitely fast. The resulting band shape of a chromatography peak is therefore affected by the rate of elution. It is also affected by the different paths available to solute molecules as they travel between particles of stationary phase. If we consider the various mechanisms which contribute to band broadening, we arrive at the Van Dimter equation for plate height. A represents the eddy diffusion, and B represents longitudinal diffusion, and C for the resistance to mass transfer. U is the average velocity of mobile phase. The mobile phase moves through the column, which is packed with a stationary phase. Solute molecules will take different paths through the stationary phase at random. These random movements will cause broadening of the solute band because different paths are of different length. The concentration of analyte is less at the edge of the band than at the center. Analyte diffuse out from the center to the edges. This causes band broadening. If the velocity of the mobile phase is high, then the analyte spends less time in column, which decreases the effect of longitudinal diffusion. The analyte takes a certain amount of time to equilibrate between the stationary phase and the mobile phase. If the velocity of mobile phase is high and the analyte has a strong affinity for the stationary phase, then the analyte in the mobile phase will move ahead of the analyte in the stationary phase. The band of analyte is broadened. The higher the velocity of mobile phase, the worse the broadening becomes. So A term is independent with the mobile phase velocity, and B term has an inverse relationship with the mobile phase velocity, and C term has a linear relationship with the mobile phase velocity. If we consider all three terms together, we could obtain the optimal mobile phase flow rate with the lowest theoretical plate height. Decreasing particle size has been observed to limit the effect of flow rate on peak efficiency. Smaller particles have shorter diffusion path lengths, allowing a solute to travel in and out of the particle faster. Therefore, the analyte spends less time inside the particle where peak diffusion can occur. This figure shows the Van Dimter plots for various particle size. As the particle size decreases, the curve becomes flatter or less affected by higher column flow rates. Smaller particle size yield better overall efficiency or less peak dispersion across a much wider range of usable flow rates. Okay, that's for today. See you next week. Bye.